try downloading it, from the HVLC.
Doesn't work. All right. I'll take a second look at it. Otherwise, feel free to record it if you guys want. I don't mind at all, in case you guys feel like it's going to corrupt again. It happens. I've been working on trying to get it fixed, but it's $5 recording software. It sucks. See. All right. Give it another minute and see who else comes in. Everyone started the homework? Hopefully not difficult at all.
I'm getting stuck on problem 3.
Which one's problem 3?
The one with the dam and the 18-foot, dam.
Oh, that's a fluid mechanics problem. It's I know you guys didn't take it, but it's
I know it's like row GH.
Yeah.
Then to get the force, you just use that.
You use the pressure distribution, yeah. What you'll find is it's a triangular distribution if you were to draw it out. And so you would just basically treat it as a cantilever beam with a triangularly distributed load, where the magnitude of the triangular load is that rho GH.
Oh, and that changes with the depth.
Exactly.
Okay.
Yeah. So, all right. Welcome to day 2 of ENS 295. Entirely forgot last class to go over the syllabus, so I'm gonna do that really quickly. Basically, every class I'm gonna be having office hours, between 6:30 and 7:30. It's after every single class. It can be here in this room. It could be in another room if you guys prefer. Or, if you can't come to office hours during this particular time frame, if you got something to do, you could always send me an email, and I'm pretty flexible with being able to meet with you guys. And, worst comes to worst, if you guys need office hours, and you can't make it, we could do, a Zoom thing or something like that. So I try and be there for you guys as much as possible. So, and I always try and respond to questions as fast as possible. I had one hiccup where a student emailed me this apparently Friday about the textbook. I lost access to my email on my work laptop, so because of that, I didn't get to it until today. So everybody should have hopefully seen the link to the textbook on Brightspace. Was everyone able to access it?
Yeah.
Awesome. Yeah, that's the class textbook. Yeah. So, hopefully you guys understand the course description and the learning outcomes already. Textbook is, of course, uploaded to the Google Drive if you guys need access to it. For the grading, there's going to be, I think it's 3 or 4 exams. Let's see. 1, 2, 3 exams. The exams are worth about 70% of the final grade. The homeworks are worth about 30% of your grade. There's no makeups on the exams at all. We all celebrate together, so be prepared for the exams. All exams are closed book, but I'm going to provide a formula sheet, which this note reminds me, I will be giving you guys that formula sheet. It's the same one that I had when I took the course, so fair game. For homework assignments, there's just a giant slew of requirements that I just basically have. Basically, be neat with everything. If you guys hand me loose leaf scrap and call it a fancy calculations, just remember in industry, clients will be paying you $150-something an hour for calculations, and if you hand it to them on a piece of loose leaf, they will be pissed. So just look through it. I know it seems like a lot, but just be organized, be nice, write out your processes. Basically, the more clarity you provide in your calculations, then the less of a chance there is of me missing something. Basically, treat your homeworks as if you were writing to a client who wasn't an engineer at all, and you basically needed to explain everything. Make sense? For the regrade policy, if you guys have questions about like your exams or homeworks, don't do it during the class time because this time is for the lectures. But if you guys do have a question, you can send me a memo, or we could talk about it after the class, outside of office hours or during office hours, just not during the main class time. That's all. And then for communication, again, I'm going to try and resolve the issue with my email, but I do have access to it on my phone. I don't know why I didn't get the announcement, the notification last weekend about it. Or not last weekend, but this weekend about the one email. But I'm usually very responsive with the emails. I usually try and get to it within like a day or so, maximum. Because I know you guys have other things going on. Sometimes you're working on a homework and you don't want to push it off. You want to try and get it done early. So I usually try to be responsive with that. And then we have a tentative class schedule. I've already uploaded a changed one onto Brightspace. So whenever there's outlying circumstances, like for example the snow day with last week, I will upload an entirely new one just showing the changed schedule. That can be seen. It should be on Brightspace already, but the one that I updated will just be a standalone document just with its updated class scheduling. The only thing that's really changed about this is I'm going to try and squeeze chapter 2 a little bit more. The topic's not too strenuous, hopefully, so I should be able to cover like 2 things in one day. All right, and then the end of that syllabus was basically just general Suffolk Community College guidelines. It's copy-pasted in every single syllabus as a requirement, so you guys should hopefully be aware by now. Otherwise, you can read through it if you have like if you have access. Everyone was able to see the syllabus on Brightspace, right? Awesome. All right, let me go here now. Now, where did we leave off? Last class, I basically did all of the notes by hand. Basically, I think some students suggested instead of doing it by hand, I'm going to present it now using PowerPoint. I will write side notes as we go along certain problems, so I should be able to, I'm able to write. So this should hopefully give you guys a better understanding. I am not an architect, so I am an awful artist. I'm very sorry, by the way, about the size of the display. If you guys have a hard time seeing, I recommend everyone just move up as much as you possibly can, even if you got to push people out of the way. And then, of course, I'm going to upload the PowerPoints to Brightspace so you guys have access. So if it's kind of hard to see here, you guys can at least just pull it up on your devices if you have them. Like I know Brianna has a tablet. I think I saw you do too. Nice. All right, cool. And I think last time we left off, we basically did the calculations. I had you guys solve the statics of the system, gave you guys an allowable stress for the problem. You determined the forces that were needed for all of the members in the design, and you calculated the stresses in each and every member. From there, I tried sketching quite miserably, I will add, all of the details and quite a bit of detail as best as I could. But you guys can clearly see, like, you've got pin connections located up at the top, as well as in the main frame over here. And then those pins we determined were undergoing shear forces, while all of the main bars themselves were undergoing tensile and compressive forces. So it really shows you how the forces transfer between connecting components and the main members themselves. This was with the joint, just looking at the pin directly in shear. Again, just as the bottom connector, so this joint here, this one that we saw was a top view of that member, which was located up there. This connection here is associated with that connection there. And then obviously this is just the end piece that's connecting both the bars together. Now, are there any questions at all about what we covered last class with shear stresses or normal stresses acting in either the bars, the pins, the methodology for solving these problems? Were there any confusions at all about anything? Or was it all pretty clear-cut with what was going on? Yes?
Could you go over bearing stresses?
Yeah. So for the bearing stresses, let's basically use this as kind of an example, right? So for these bearing stresses, you could see that, not even on bearing stresses, you could see that D, D prime, and E, E prime are shear planes. So those are where shear stresses occur. Now, this example didn't cover bearing stresses, but when you have a system, these pins are undergoing bearing stresses also, which that bearing stress is entirely just bearing along these surfaces here. So to find the bearing stress is just a type of axial load directly along the surface. So if we were to draw out what it looks like in cross-section, what the bearing face looks like, it's basically just this face, but rotated. So I'll try and draw it out the best I can. So this might be that D prime face. And then this would be the E prime E face. And so your bearing area is just basically the cross-sectional area perpendicular to the force, which in this case would just be the diameter of that pin, we'll call it dB, multiplied by basically the thickness of this material here. So that thickness is really what's governing. If you look carefully, it's a rectangular cross-section. So the area that's subjected to bearing here would just be the bolt diameter times the thickness of the connecting plate. And then obviously you would use force equilibrium to analyze the internal force, which pretty self-explanatory is just going to be that force FB, which from the last class, that force FB is just going to be the 40 kilonewtons divided by 2. And the reason it's divided by 2 is because there's two bearing surfaces, so the force gets distributed between the two surfaces equally. Does that make sense?
Yes.
Awesome. Are there any other questions about this at all? This example that we covered last class? Yes.
I'm just a little bit confused with the drawing. So where on the pin is the bearing force or bearing stress actually like taking place?
The pin itself is, well, it's occurring both on the plate and the pin. So if we take a look at this drawing, for example, you have a compressive force basically applied right there. So that means that you are going to have bearing from the bolt.
Okay, I see it now. Yeah.
Right. Now, vice versa, you're going to have the plate equal and opposite force.
I don't know like what plane it would have been on.
Yeah. So bearing is basically occurring on those three planes.
So that's also where the shear stress is occurring though also. Right?
Shear stresses are occurring along this plane on the pins directly.
Got it.
It's a matter of orienting the areas. So it could be a little confusing. It's all right. All of it's got to get checked regardless. Any other questions? Awesome. All right. And then this kind of goes to show a little bit about the force equilibrium also, similar to previous, but we basically covered all of this already. All right. Now, continuing from last class, we know that stress is equal to force divided by the cross-sectional area, but that stress is ultimately dependent on what area you're really considering. it's all dependent on the orientation of the plane, how you cut a certain section through a particular member. One such example is if you cut a plane through an oriented rotation. For example, this could be something like a weld line, like if you're connecting two elements together through a weld and transferring axial loads, that plane could be a representation of a weld that's inclined. So, because of that, you're going to have but you're going to have both shear stresses and normal stresses acting on the system, where your normal stress is going to be the force that is directly perpendicular to the plane here. That would be your stress sigma. And then shear stresses acting parallel to the plane equaling tau. Now that area that we have is just going to be a rotated area. So that's what this A theta is. So that is not necessarily the cross-section of the element itself, but instead now the oriented cross-section. So when you geometrically analyze this, you're going to have a force with its associated components. So it's going to be the force P times its angle cosine theta. That cosine theta coming from this orientation here gives you F. P cosine theta gives you F. And then the area is just going to be A naught divided by cosine theta, which in turn should give you P over A cosine squared theta. Does that make sense? You're basically having to rotate both the area and the force in order to find the stress, which is why you have a cosine squared component instead of just a cosine or a sine value. And then you would do the same thing for the shear stress, which just breaks it down to sine theta, cosine theta. Are there any questions about this at all? I know the image is a little small, so I will try my best. And please bear with me as I continue to learn how to use this product. Clear pen markings. Nice. And now I can zoom in. There we go. Awesome. Now, the stress depends on how you cut it. So the stress, if you plot it out, depending on how you orient it, then you would find that the normal stresses can go anywhere from the main stress, P over A, all the way to 0. That's if you were to take like if you had a rectangular cross section here, and then you cut a cross section just like that, and then you applied your axial force here. Obviously you can't have a normal force because the normal force would need to go that way. So because of that, that's why you have it where you have a 90-degree rotation. That's that pi over 2 orientation. That's why the normal stress is 0. For shear stresses, they just act directly in conjunction with it. So it really emphasizes how the plane that you're considering orients it. So I'll just give you guys a good example. We have just like a wooden block. It's subjected to a 2.2 kip force. It's supported by 2 wooden members of uniform cross-section. They're joined by glue. This is similar to when I was saying 2 members connected by a weld. So 2 wooden members end spliced at the indicated location in the green. So this area here is that glued location. And then we need to basically determine the normal and shearing stresses in the glue. Just using the equations that we had previously derived, you can plug these in pretty easily. So ignore that. I don't know what that is. That's probably one of the answers, but it's just not labeled properly. So for the normal stress that's acting along that plane particularly, we can draw it out in a section view. where this would be your normal stress. That would be your shear stress. And so sigma would just be the 2.2 kip force. The main cross-sectional area is just going to be the 5 times 3, so 15 inches squared. And then cosine of the angle of rotation is going to be 30 degrees. I don't know why I wrote, whoops. There we go. Of 30 degrees squared. With that being the angle of rotation. All right. Now you throw this all into a calculator. Whoops. And you get that the normal stress is approximately, I don't think that's right. Did I do that right? Where am I going wrong? I'm already messing up. Oh wait, no, I'm right. That should give you 0.11 KSI, which is where that 110 PSI comes from. Now, if you were to calculate the shear stress, let me do that in blue if it wants to. There we go. Now, if we wanted to do the shear stress, 2.2 kips divided by 15 inches squared, sine of that 30 degrees, cosine 30 degrees, that shear stress is just going to end up being about 0.064 KSI, which is 63.4 PSI. And that's it. So you would just need to basically design the glue to handle both the normal stress of 110 PSI along with the shear stress of 63.4 PSI. And you would compare that to whatever the product capabilities are, and yeah, just pick whatever satisfies both conditions. Any questions about this example at all? It's a simple plug and chug equation. Does anybody need me to re-elaborate on the equations at all, or all good? Awesome. All right. Now, when we consider stress under general loading, force and area are all just various different components. It's all dependent on a particular plane that you're considering, but these equations all just are heavily dependent on the orientation that you're considering. For example, stress acting on one face might be different than a stress acting on another face in a 3D plane. That's where you get very complicated equations like this, where basically each face has its own vectorial components. Matter of fact, stress is actually not even a vector or a scalar. This is probably going to be a new term for you. But stress is what we call a tensor, which basically just means it acts in 18 different directions, or there's 18 different orientations that you could consider. You would have a normal stress in the X, Y, and Z directions, and then you can have shear stresses acting in 2 directions per face. And then obviously, if you were to orient that block by like 180 degrees in every single direction, or look at the opposite side of that, you're going to have stresses that have to be in equilibrium. So because of that, you've got stresses going that way, that way, that way, and then stresses acting in the exact opposite directions. And then when you do, obviously, force equilibrium, you would find that the stresses acting along the XY plane, so that would be this stress and this stress here, they have to equal each other in terms of magnitude. Now, stress is going to obviously have its own sign components. For example, when you guys were dealing with compression members, how did you guys deal with, not compression members, but truss members? You had compression and tension members, and you basically looked at the direction that the forces were going with respect to either the joints or with respect to the members themselves. In a similar way, we have a general orientation for stresses to occur, where basically anything that acts in tension would be considered positive, anything that acts in compression would be considered negative. What I personally like to do is generally just look at this face here and this face here, and then this here would be sigma x. Sigma x is acting in tension from that face there, so this would be positive in orientation. This sigma y is acting positively from this face here, so that would be positive in orientation. But then the question becomes, how do we identify if it's a positive or a negative shear stress? Well, that's when I look at both of these here. And what we should have is basically the stress is all going to this corner point here, and we should find that the stresses will be positive in that orientation. You could think of it like as if you've got a plot here. This is your x and y curve. You have a positive value and a positive value leading to there, so it's a positive value. That's why, in a similar way, when you have 2 points going negative, negative to a negative, what's a negative multiplied by a negative? It's a positive value. Now, if we were to look at stress from a different orientation, like, for example, if we had a shear stress going that way and a shear stress going that way, one is going positive right, one is going negative down. Positive times a negative is a negative. I've got some examples coming up on the next slide. So, take a minute, try and identify if the stresses are positive or negative really quickly, and just raise your hand if you think you've let's just go over it in the class. I'm not going to ask you guys because this is going to be like 30 seconds. What do you guys think sigma x is going to be? First, who can tell me what sigma x is?
Is it just 30 megapascals?
How many?
Megapascals? 30?
Yeah, 30 megapascals. Positive or negative?
Positive.
Awesome. Who's got sigma y? Yeah.
20 megapascals.
Positive or negative?
Positive.
Positive. Who's got tau xy? Yeah.
Would be 10 megapascals and positive.
Yes. Awesome. Let's do this one now. I'm going to say tau xy. Let's make the magnitude for this one 30 MPa. It's missing. Who here's got it? What's sigma x? Oh, wait. Whoops, my bad. I'm orienting wrong. It's already written out. My bad. I'm looking at it wrong. What's sigma x? Yeah.
0?
Yeah. Confused me too.
No,
Well,
I
it
was
just confused me.
by
The arrows, yeah.
the other one.
To be fair, this is also the first time I'm looking at this. I've looked at every other PowerPoint except this one. So, excuse me if I mess up once or twice. First mistake in a semester. What about sigma y? 20? That's what you said. Positive or negative? Yeah, positive. And then tau xy. Yeah,
Would be 10
Negative 10. Awesome. Here's another one. Or is this just a copy paste? This is a copy paste. Oh wait. Ooh. That's different now. If you guys pay close attention, look at the coordinates. It's changed now. You've got an XZ plane. So, who here can tell me what sigma x is going to be? Yeah,
30.
30, positive. What about sigma z?
20.
Positive or negative?
Positive.
Negative. Positive z is going downwards for this face. So you would always look at this face and this face, but the issue is that positive z is being defined as downwards, so because this z is going upwards, it's negative. And then tau xz. What do you guys think? Yeah,
It'd be -10, -10.
awesome.
Wait, is it positive?
What?
Is it positive?
Nope, negative. Reason
Oh, 'cause
being,
it's Z.
yeah, so it's also dependent on the coordinate system.
Would sigma y for this be 0, or you just can't assume that?
Basically, yes. When it comes to determining all of that, you would need to look at it from like a cube perspective. So you can't really, you would just assume that it's 0 because obviously it's not defined here.
Yeah.
And then we've got one more, but I'm sick of that. All right. So, oh man, it's showing. Crud. Nobody look. Ignore it. All right. Here's the 3D example. We're going to have sigma x, sigma y, sigma z, a tau xy, which we know tau xy is the same as tau yx. Tau xz has to be the same as tau zx, and tau yz is the same as tau zy. No, don't look. Don't cheat. All right. Real quick. What's sigma x going to be? Who can identify which one sigma x is? Yes. Let him. You go.
-10.
-10. Yeah, so this is going to be sigma x is equal to -10. What about sigma y? Which one's sigma y? It's an easy one. 20? Yep. Sigma z?
Positive 30.
Awesome. Tau xy. Yeah,
Positive 25.
wrong sign.
Oh, -25.
It's -25. And that is because positive x, positive, I drew it backwards. Positive x, positive y. This is going negative x. Oh, whoops. Negative y. So, positive x, negative y. Blah, I can't speak to the life of me. It's supposed to be negative because if you were to look at it from this bottom face here, you would get that this shear stress would be going to that corner. So it's positive x on that face. So you have it as -25. What about for tau xz? Who's got tau xz? My thing is absolutely not calibrated in the slightest bit. Yikes. Well, you guys have basically seen this enough times, so I'm just going to give up on this. I hate PowerPoint. Tau xz is basically just going to be the positive 15 megapascals, because if you were to look at this from a top view, the z coordinate and the x coordinate are going that way. And so it's heading towards a positive coordinate location, hence why you have it as positive. And then when you do the same thing, looking at the YZ plane, you would find that it's going to a positive coordinate location. Does that make sense? Any questions about this? Yes?
So on a 2D plane, even though there's like 8 vectors, there's only 3, you get an X and a Y for normal stresses, and then 1 shear stress.
There's basically 3 normal stresses and then 6 shear stresses, but 3 of the shear stresses equal another 3 of the shear stresses. So you only technically have to really put down 3 normal stresses, 3 shear stresses.
For 3 dimensions, right?
Yeah.
Yeah. For 2 dimensions, it's like you cut that in half and it's only 2. 3 max?
You would only have 3, sigma x, sigma y, and then a tau xy, or whatever planes you're dealing with.
Okay.
Does that make sense?
Yeah, and they point towards the pointers.
Exactly.
Okay.
Yeah, the shear stresses are always going to point towards the corners. All right. Now the fun stuff that you guys have been waiting for a while. Design considerations. You guys are going to learn how to design in this class. All right? Many of you have probably heard from Professor Dawson, yeah, just design it with a large factor of safety. It'll be okay. You guys might have been wondering, what the hell is a factor of safety? Basically, the factor of safety is defined as whatever the ultimate load is, which is the capacity of a given material, over the allowable design load, which is the force that is imposed on it. So the factor of safety can, in simple terms, be defined as capacity over demand. So if you've got an anchor bolt holding a piece of electrical equipment off the top of a tunnel roof, and that anchor bolt is able to hold up to 2,000 pounds of tensile force, and only about 500 pounds of tension force is applied to it, your factor of safety is going to be 2,000 divided by 500. You've got a factor of safety of 4 on it. All right. Another way you can kind of consider it is basically sigma allowable has to be, let me rewrite that. Capacity divided by demand. So then sigma U, which is the ultimate stress that a material can undergo, has to be greater than or equal to the applied force divided by the factor of safety. Is that right? No, multiplied by the factor of safety. Yeah. For those of you who are civil engineers interested, this is something that you'll see in codes known as allowable stress design. So if you guys once you start getting into your concrete design and steel design, we call it allowable stress design. We have also load and resistance factor design, where you have factors applied to both the capacity and the loads. So there's 2 different design methodologies, but you should get roughly the same answer towards the end. You'll learn about that next year. All right. And again, never mind. All right, so I've got an example here given that a material of member AB has an ultimate normal stress of 450 megapascals, we need to determine the cross-sectional area of said member to provide a factor of safety of 3. So, how do we determine this? First, you need to determine the force equilibrium. You guys will notice that there's a hinge located at B. So hopefully when you guys went over frames within your statics course, you realized you're supposed to break it up at the point of the pin, and then you analyze the force equilibrium there. So in total, when you do that, you should get a tensile force of 21.6 kilonewtons acting within bar AB. From there, to design it, you can either do one of two things. This example considers the allowable stress of 450 megapascals and just divides it by 3. So it's saying, even though it can handle 450 megapascals, we don't want to exceed 150. Another way that you could have done this is just simply computed the force with a factor of safety of 3 and just multiplied the 21.6 kilonewtons by 3. And that would have given you an ultimate design force of 64.8 kilonewtons. So that's the force that it would be designed to handle. From there, that stress that you calculate, sigma DES, would just be the 64.8 kilonewtons divided by A. But instead of it being the sigma DES, and my thing's not working again. Awesome. The sigma DES in this case would just be the 450 megapascals. Because again, the factor of safety is applied directly to the load. Now, when you solve for A, you will get the same exact answer. It's just a matter of which side of the equation you're applying the factor of safety to. Are there any questions about this example at all? Yes?
Where did all the numbers come
All the numbers?
from? Yeah.
Like 9.6.
The 9.6 kilonewtons comes from the 8 kilonewtons multiplied by 1.2 meters. So for a distributed load, think of it like a cross-sectional area. You've got the magnitude of the distributed load acting directly on the center here. So that 8 kilonewtons per meter, the entire length of that bar is 1.2 meters. So that 9.6 kilonewtons is the same as saying that 8 kilonewtons per meter multiplied by the total length that that distributed load is applied over. Right. And then when you take moments, are you the one that didn't take the statics course? See me after class because I got to ask you something. But basically, when you take moments, it's a force multiplied by a perpendicular distance, which the perpendicular distance in this problem here is just basically where this pin is to this force here, which is 0.4 meters divided by 2.
Gotcha.
And that's the location. Are there any other questions about this problem? Nope. All right. Last step. I'm not even going to bother trying to hide it anymore. I give up. All right. We've got a steel plate. It's a 1/4 inch thick. It's embedded in a type of concrete. All right. You actually see these a lot within like a lot of hanging structures, especially. We have a plate. It's got a 3/4 inch hole located, and the ultimate strength of the steel used is 36 KSI. This is a type of A36 steel, I believe. Now, a factor of safety of 3.6 is desired when the force, which this P right here, is specified at 2.8 kips. All right, now we want to neglect the normal stresses between the concrete and the end of the plate. So basically, all we want to consider are the stresses of this embedded region here. So all of this, ignore. That's an entirely separate part of the problem. That would actually you would need to consider the additional stresses of around the hole itself, which that's an entire project in itself. So we're only considering basically what the stresses are built into the plate itself. All right, we want to determine the required width A that the plate needs to be. This stress, it's actually kind of labeled wrong now that I think of it. No, that's right. I was thinking it was a shear stress, but it's not. All right. So, we want to determine what the maximum stress on the plate is. You first take the allowable stress, which the allowable stress is, not the allowable stress, but the maximum stress the plate can handle is 36 kips per square inch. That's what was specified as the sigma U. We apply a factor of safety of 3.6 to it, so that means we limit the amount of stress that can be applied. So 36 kips per square inch divided by the factor of safety of 3.6. That plate cannot handle any more stress than 10 KSI. From there, we can determine the area that we need, because again, we're trying to determine this dimension A for that problem. And from that, we first need to know what the area is. So, how do we find the area? If we cut a cross section directly through the plate, and we call this the cut, and we look at the cut here, what we will have is a dimension A, and the thickness of the plate we know is 0.25 inches. Everyone sees where that section comes from, right? So, this entire area is some value A, which the problem computes as the force divided by the stress. You get that the area needs to be at minimum 0.28 inches squared. From there, if you wanted the dimension A, this problem is explicitly actually accounting for the hole, so that's the area that you would need there. But if you didn't account for that, you would get a different value. With the hole accounted for, then you would basically just subtract the area of the hole here, which is where that A minus D times T comes from, where this value is the D. Everyone sees that? And so from there, we find that once you plug in A minus D over T and calculate, we write it out, you should get 0.28 is equal to A minus the 3/4 inch plate, or hole, I mean, and then the plate itself is 1/4 inch. Use algebra, you find out that the plate has to be 1.87 inches in width. Now, what if the hole wasn't there? What do you guys think the area would be? Think you can calculate that for me real quick? I'll give you guys a few minutes to figure it out. Everyone understands what's going on here, right? Or do some people need emphasis? I might not have explained it clearly enough. Yes?
Would it be without the whole just 1.12?
1.12. It should be a smaller area for sure. So 0.28 divided by, yeah, it's 1.12. Because at that point, the hole isn't contributing to any stress reduction. So, yeah. Does everyone else get 1.12 inches squared? Nice. All right. Let me freeze this, and then I'm actually gonna have you guys try and figure this out. Let me see. Is there a way that I can block this without you guys seeing it? That's what I need to know. I'm gonna keep that. Insert a shape. I just unfroze it, please tell me. Awesome. All right. Now, we determined the dimension A that we needed. Now what I want you guys to do is tell me what the required dimension B would need to be in order to be able to prevent this from ripping out of the concrete. All right. So I give you guys that the ultimate bond stress between the plate and the concrete is 300 psi. So what you guys need to do is determine the minimum depth into the concrete in order to prevent the plate from ripping out of the concrete. Use the same factor of safety as the problem previously. This factor of safety was 3.6. I'll give you guys a few minutes to try and figure that out. Once you got an answer, just raise your hand. I'm curious to see what you guys get. Really quickly, what type of stress would this be causing? Yes. smart with it this time.
You just highlighted over you. You're trying. Sounds like a pretty large.
Should also probably. What is everyone using for A, by the way? Everyone's using the value that was in the last example, right? That's in case you guys need it, it's 1.87. If you did it with the other value that I had asked you guys to do it, that's fine too. I just want to make sure you guys are grabbing the right areas. Because that's where stress has kind of become a little more confusing, is figuring out what areas to use. I'll give you guys like 2 more minutes. I think that is the thickness, yes. All right, let's go over it. What did you guys get for the area? I think that's the real question here. What is the area that's subjected to shear? You said it was a shear stress, so I want to see who's got the shear area. The area subjected to shearing force. Yeah.
33.6.
How do you get that?
Kind of, in the problem before, we used P divided by, sigma roll. So I did the same, but instead of sigma, it was the shear stress. So I
Yeah.
found the shear stress.
Yeah, so the shear force in this case would just be that P value, which was 2.8 kips. Now, the allowable shear stress is just going to be that 300 psi, and you divide that by the 3.6 factor of safety. And that should give you 83.3 psi. Everyone follows so far, right? Awesome. Now, we want to calculate what the area is, and I presume the area you got from the 2800 divided by the 83.3, right? Yeah. Which gives us the 33.6 inches squared. Awesome. Now the trick becomes, what does that area look like? Who here has the guess? Yeah.
Split between two surfaces. So there's like two.
Top and bottom, right? Yes and no. There's side surfaces too. Yep. So, what he was saying is you have both a top surface here that's subjected to shear. It's reflected on the bottom as well. But what you also should note is the fact that you've got a side surface just like that. And that's reflected on both sides of the plate as well. All right. Now, most times for concrete, you would generally just consider the shear planes. In some instances, if you're using like a special grout with a tensile strength, you could also consider some type of net stress here, but we're just ignoring that for simplicity of this problem. So things can get pretty complicated really quickly when you start considering all different stresses and forces acting on certain things. So now what we need to know is what is the value of that area. That area we can write as A times B, and then obviously there's two of those, top and bottom, plus the thickness of the plate times B, BT, and then it's reflected on two sides. So this can be rewritten as 2B times A plus T, which we already know what B and T are. 2B, A we calculated as that 1.87 inches, right? And then T was the 1/4 inch. Which this should give you 4.24 B. So 33.6 is equal to 4.24 B. Which will give you B is equal to roughly 7.92 inches. Now, in case my handwriting is atrocious, here's what it looks like. Questions about this? And I know that this board is, again, hard to see. I've tried zooming in on this as much as possible. Yes?
Can you go over the factor of safety again?
Yes, absolutely. So the factor of safety can either be applied in two different ways. The factor of safety can either be, let me go back to this slide. And it didn't clear any of my pen markings. Awesome. Clear. No. Whatever. I'll keep these. And I'll just add another slide. Don't worry, it's going to pop up. It's going to pop up in a second. Don't worry. I hope. Yes, it is. All right. So the factor of safety can either be applied one in two ways. I'm going to cut it down right down. You can either apply it directly to the strength of the material, where when you have the equation, it would be demand, which has to be less than or equal to the capacity of the material divided by the factor of safety, or to the load, which then would just be the demand times the factor of safety has to be less than or equal to the capacity of the material. So it's always going to be one of those two options. Both options are correct. They should lead you to the exact same answer. It's just a matter of how you apply it. In most of the problems that we did today, we did it where the capacity was divided by the factor of safety. If we applied this to a design case where we're multiplying it to the load, then what we would actually have is, instead of it being like this, where now it's not letting me keep my, I don't know how to clear this race. Okay, that's good enough. Yada, yada, yada. Oh, wait, let me do that. Because technically all this is just going to be the same. Basically, your design shear force would just be the 2,800 pounds times a factor of safety of 3.6. So you would be designing for a shear force of 10,080 pounds. And then your tau would just be directly that 300 psi without any factor of safety applied to it, which then will just give you 10,080 divided by 300, which will give you the exact same thing. So 2 ways of just approaching the same question. Does that answer it?
Yeah, one part, and then I do know the difference between like the demand and like the capacity. Like we did the calculations and we found the capacity, or
The capacity is always generally going to be a given material property. So for example, for an A36 steel, you might have a yield strength of 36,000 psi. That's a given, that's a known. If you're calculating for what the capacity needs to be, that would then give you the ability to look on a product data sheet and determine like, okay, this is the strength that I need. For example, if you compute, you need a steel that can carry 30,000 KSI, and you find a steel that can carry 60 KSI, you're good. For like demand, on the other hand, demand is usually what you need to carry. It's what the system demands, right? So if it's like, I need you to carry 2.8 kips, you have to carry 2.8 kips. Does that make sense?
yeah.
All right. Any other questions about factor safety?
Just go back to the one we split it, yeah.
This one.
Yeah.
Let me just go on this slide and zoom in on it. Not that you've got like the text boxes blocking it or whatever. Yeah. Yeah. In a lot of cases, you would call something like this in like industry, if you're a civil engineer, like a strength reduction factor, and then you would consider the factor of safety for loads a load factor. So if you work an internship and you hear load factor or strength reduction factor, that's what it means. It's just, are you using ASD or LRFD, which is how are you applying the factor of safeties? And that's not necessarily explicit to civil engineering. I just am talking from my own experience. All right. And then obviously the factors of safety, those are generally like a code requirement. For example, like I've designed elevator equipment for certain tunnel projects, and certain elevators actually like require like a factor of safety of like 10 because they're that critical. You know, so like you might have a weighted capacity of an elevator of like 3,000 pounds. You're designing it for 30,000 pounds because you do not want those cables to crap out while somebody's in it. Anybody want to take a guess what the factor of safety of a structure like a bridge would be? What is your guess? You just said something. No.
Oh, me?
Lower than 10.
Lower than 10? Yeah.
Lower than I would expect.
What do you think?
5.
5?
25.
25? Who here's got some values? Come on.
2 or 3.
You're dead on. It's 3. Now I got a good one for you. Factor of safety of an airplane.
4.
4? No. Nope.
Well,
Much.
1.
1 would mean designing directly to the capacity.
That's what phone goes.
1.1.
Yeah.
There's a 10% tolerance for airplanes. Anybody want to take a guess why?
Keep it light.
Don't they have?
You have to keep it light. So that's why when you're designing an airplane, you have to use very advanced computer software in order to analyze the forces. Not to mention the geometry of most airplanes is relatively complicated. So for those of you who are pursuing mechanical engineering, you would take courses like aerodynamics. I never took those courses. I took like fluid dynamics, so it's kind of similar, but I mean, I never learned how to calculate thrust forces off of an airplane wing before, but I can imagine those forces would be pretty massive. Yeah, so that's factors of safety for you. You have about 5 minutes left, so I am actually going to torture you guys a bit more and just hop into basically the next lecture just really quickly, especially since I just kind of want to see if the PowerPoint even works. No idea how to open this. Let's see. Chapter 2. All right, so this is a bit of an introduction on what we would be going over more in detail next class. Basically, stress and strain and axial loading. Now, we learned about stress, right? Force divided by area. And explicitly, this chapter is going to be focusing on axial loading for the most part, because axial loading is a very complicated thing once you get into the nitty-gritty of it. And then shear loading is, all the equations are nearly identical. So once I teach you guys this, you guys will basically know shear as well. But we learned stress. Anybody want to take a guess at what strain is? Have you guys heard of the term strain before? And I don't mean strained as in like strained for time for exams, all right? What's strain? Y'all have heard of it, but can't tell me what it is? Come on. Strain is basically deformation. So, in this chapter, I'm going to introduce the concept of deformation and strain. This discusses the relationship between stress and strain using Hooke's law. Everyone has hopefully heard of Hooke's law, right? Springs. Well, what you guys will see is materials behave, we can approximate them to behave exactly as springs, at least for small deformations. So that's an important note that I would add here, is that this is applicable to small deformations. Right? Because once you start getting into like really large deformations, you get nonlinear behavior, and then at that point, it's very hard to approximate without a computer and running probably about 1,000 iterations of calculations just to get a somewhat accurate answer. It becomes an absolute nightmare. I'm going to introduce a new constant, or a few new constants, I should say, for elasticity, specifically the elastic modulus, we call it. This is going to be a new concept to you guys. It's a material property along with Poisson's ratio. Has anyone heard of Poisson's ratio before or no? No. All right. Basically, those terms relate stress to deformation as well as deformation in various different directions to each other. You could think of it like if you were squeezing a hand full of Play-Doh, right? If you were to squeeze it, it'll expand and contract in certain directions. Poisson's ratio will help you identify that. Obviously, for like a member like steel or concrete or aluminum or something like that, it's not going to bend like Play-Doh, at least in an elastic regime. Some of you guys might have seen those hydraulic videos of shit just getting crushed up and squeezed. Not going to be dealing with stuff that complex, all right? We're going to use the axial deformations to solve for statically indeterminate problems. Who has heard of statically indeterminate members before? Professor Dawson has likely explained that before, right? Where, I'm not going to explain it, but I want to ask you guys, what is the difference between what is the main assumption that you guys had when you were taking your statics course? Everything was statically determinate, right? What does that mean? Yeah.
We define all the forces and like, all the members and the reaction forces using our equilibrium equations.
Exactly. Now, what's the difference between that and an indeterminate problem?
There's not enough equations to find all the forces.
Exactly. Which is why we have to use axial deformations. This is a concept that is commonly referred to as compatibility. So, and we do that using Hooke's law. So, for every force, there's going to be an associated deformation. So what you can do is you can calculate what the deformation would be as if it was unrestrained. And then obviously, if you're pushing it up against the wall directly, then equal and opposite force, you can correlate that to what a deformation would be if the wall wasn't here. And that reaction force would basically correlate to whatever deformation would exist. Does that make sense? We'll see problems next class. We're going to introduce St. principle. Kind of hard for me to explain that right now. Introduce stress concentrations. So if you guys remember the last problem that we were just looking at from the previous chapter, we had the giant hole that was located in the plate. That will actually induce stress concentrations around the opening because there's nowhere for the stresses to go. So this kind of results in a somewhat nonlinear stress distribution because you would imagine that the point of breakage would be closer to the holes than away from the holes, right? We're going to study plastic deformations. I love plasticity. That is a very fun topic for me. That's outside the region of the linear elastic approximations that we do here in this class, but I'm going to show you guys a little bit about what plasticity is. And yeah, we're beyond time, so I am actually going to leave this blank page as blank and keep you guys wondering for our next class. All right. Sounds good. Does anyone have questions about the homework? No? No questions? It is due on Wednesday. Hopefully everyone's looked at it. I don't think it's too bad. It's mostly just a review of statics, from what I recall. And then I threw a few stress problems in there as well. Yes?
What about use loosely? I mean, like,
Anything you can use, just not loose leaf.
It's not loose leaf.
Yeah,
Okay.
I hate loose leaf.
Okay.
Especially since, like, I use a marker. I like to grade with a marker, and loose leaf will make the marker bleed. So because of that, just, yeah, don't do it.
Okay.
It just makes it easier for you, easier